All right, so I finished my general announcements, and students should turn in their linear regression packet. If you haven't, you have exactly 2 days to get that in for late credit. We're going to start on 3.215. As a heads up, we will skip 3.216. I'll explain why when the time comes. All right, now before we get into the actual problem, I wanted to share some background information. I doubt many of you have ever heard of 16 handles. You have? This location has closed, but I would imagine more of you have heard of Sweet Frog. Okay. So 16 handles is kind of like a Sweet Frog. You walk in, there's basically a buffet line of frozen yogurt flavors. You just grab a little cup, you take whatever flavor you want, you head to the fixins bar, and you take what you want. And then you are charged based on the weight of what you got. Now, my wife and I, many years ago, went here and I took pictures of what we got and recorded some information because I could use this in a stat class. So this is my wife's. She got birthday cake, frozen yogurt, Reese's Pieces, crushed Butterfinger, and rainbow sprinkles. Love my wife to death, but that doesn't appeal to me at all. Mine was a mixture of 3 different frozen yogurts: coffee, peanut butter, and chocolate, cookie dough pieces, raspberry truffle chocolates, and brownie bits. That to me sounds way more appetizing. Now, and I got my wife's permission to share this information with you. At the time, she weighed 132 pounds, and her cup of frozen yogurt was 8.4 ounces. At the time, I weighed 220 pounds, and my cup was 12.6 ounces. And that got me wondering, if I were to talk to customers as they were leaving, after they purchased their ice cream, and I got 2 pieces of information from them. How much ice cream did you get in terms of ounces, and how much do you weigh in terms of pounds? If I got that information from a bunch of people, what would the relationship look like, and how strong would the relationship be? So, just out of curiosity, would you all expect that relationship to be positive or negative? Positive, I would agree. I would say that those two variables definitely move together. Smaller people, such as little kids, typically are going to get smaller amounts of ice cream. Larger people, adults, are going to get more ice cream. And then obviously, ages in between will vary. Okay. So that's sort of the thrust of this initial question. Mr. Oben imagined placing a scale by the register to weigh customers as they pay, perhaps implanted in the tile on the ground so as not to alert them, in hopes of finding an association between the weight of their frozen yogurt and their own body weight. Side comment, which is this is foreshadowing for chapter 4. So what I'm about to say has nothing to do with chapter 3. The reason I came up with the idea of implanting a secret scale is because this is going to help me avoid bias. Okay. How much ice cream a person gets is objective. I just wait for them to pay and then I look at the receipt or I get it from the employee or whatever. You can't really lie about that. But if I ask a person, how much do you weigh? Number one, they might not want to reveal that. And then I have to worry about what's called non-response bias. I have to worry about the people that don't share that information because they're not comfortable with it. Okay. And how is that going to throw off my data? How is it going to make it so that my data is not truly representative? Okay. Use Mr. Oben's description of what he imagined the association might be in order to sketch a scatter plot. So take a minute and do that yourselves now, please. Go. So first thing, remember I said before that if I asked you all to draw a circle, draw a less perfect circle, some small one, someone draw a big one, but the bottom line is we'd all basically be drawing the same thing. That's the idea with this, which is why I put these dots in green. I have no idea what you chose to draw, but as long as it's clear that it is a positive relationship and it is like there is something going on there, it's weak. It should not just be a giant cloud of points that fills your paper. That would be a problem. There needs to be a clear, like as this thing goes up, this other thing tends to go up. And then, of course, you can have a couple outliers. Okay. Now, believe it or not, and my wife has gotten used to my weird oddities when it comes to being a math nerd. This is not made up data from real people that I asked when we went to Sweet Frog, when we went to 16 handles. What I have found is that if you lead with the statement, I'm a math teacher, I'm trying to collect data for my students that I can use in the classroom, people are much more willing to open up to you. The other thing, and this is to avoid bias, so I'd go up to somebody and say, hey, I'm a math teacher trying to collect data. Could I just know how much ice cream you bought in ounces? And some of them would just tell me, but most of them didn't know off the top of their head, and they'd show me the receipt. Then I would ask, I also, because I'm trying to build a relationship between data, I need your body weight. And at that point, it's like they're already invested because they already gave me some data. And so they are more likely to give me the data. The other thing I want to admit to you is that I talked to about 20 people. So this is not all 20 people. I hand selected just to give us a more fluid curve, just to make the lesson a little easier to work with. Okay, so I did jury rig the data a little bit. All right, so use the linear model to predict the amount of frozen yogurt a 300-pound person might typically get. Comment on the reliability. There's some parts of today's class that I'm not going to give you time on, because I imagine if I gave you time on them, you should all be able to do it easily. This is an example of that. So all it is plug in 300 into the model that's provided to you, type a couple buttons, get the prediction. Okay. What's more important to me is, can you all help me respond to the question where it's telling us to comment on the reliability? Now, again, if you're ever asked to comment on the reliability, it's kind of, you're being asked to make a decision. Is this a reliable prediction or not? Okay, I'm going to give you what I consider to be the low-hanging fruit. No, it is not a reliable prediction. But I'm wondering if you all can help me out with the two different reasons that you could argue for why this prediction is not reliable. I'm going to volunteer one of the two reasons. All right, so we got the two things. So Arnav mentioned we have curve data. Now, one of the other things you could say, and I'm going to talk about this later today, you could notice that the middle, like 5 or 6 points, it looks like 5 points, are under the line. And what that means is the actual data is lower than what that linear model predicted. So if your body weight is somewhere between, looks like maybe 120 to like 250, this model is over predicting how much ice cream you're probably going to get. And then the opposite is happening with the other points, which have positive residuals. In those zones, it seems that the model is under predicting how much ice cream you're probably going to get, because the points kind of curve up above the line. So these are residuals that are not random. That's going to be an important part of today's lesson later on. Okay. So that is the other way that you could kind of say exactly what Arnav talked about. He said, well, it's curved data. This is a linear model. That doesn't make any sense. You could also just talk about the non-randomness of the residuals. The residuals are curved. But then I also went ahead and said what Kevin mentioned, which is we're extrapolating. The heaviest person I talked to was 262 pounds. Okay, so you can't use data that stops at 262 to then try to make a prediction to 300. You might be right, but only if the pattern you've seen get established continues forward. And that's what we call extrapolation. You're literally hoping the pattern you've seen so far continues forward. Okay, or backward. You know, my lowest person that I've included is 56 pounds, which means you shouldn't use this to predict somebody that's smaller than that. Either way, you're extrapolating. Okay. Questions before we turn the page? All right, go ahead and turn the page. I know that directions say to, oh, actually, we'll get to graphing those points later. All right, so this says show work for how to find the residual in the chart below. Can anyone explain to me, and let's just make sure that we understand how to read this chart, because it references the first residual, which is 0.851. What that first row is telling you is there was a 56-pound person who got 6 ounces of ice cream, and that turns out to be, because it's a positive residual, that means that person actually got more than what we thought they were going to get. But the question I'm asking you all, and I'm hoping somebody can volunteer here, can you explain to me how to get that 0.851 number? Like, if it wasn't there, how would you calculate it? Perfect. You'd have to use the weight of 56 pounds with the model that was given on the previous page to say, all right, well, this is how much I thought a 56-pound person. Okay. And then you'd say, well, this person actually got 6. And remember, residuals are always actual minus predicted. It's always that order. So they actually got 6. You thought they'd get 5.1, and that's where the positive 8.851 came from. Okay. We don't have to interpret it. That wasn't part of the directions. The reason I take a moment to stress this particular mathematical process, which I'll be clear, at this point should be easy for us. And if it's not, maybe I was moving too fast and you got to ask questions. Okay. But the reason I highlight this is because, as I said, today's point is, can you build residual plots and can you understand why they're useful? Well, if you can't get these values, you can't build a residual plot. Okay. Now, before we actually get to part D, it says plot the residuals. So we're going to get the residual values and we're going to plot them. The first one was 0.8 something, so it's kind of right in there somewhere. But before we get to that, I want to stress that just like yesterday with the whole cucumber precipitation graphs, hopefully you all recall the importance of paying attention to the labels on the displays. That is always going to be true for residual because there is no standard of what the X variable has to be. It could be the actual body weight. It could be a predicted body weight if you have access to that. Or very often, since you're talking about a residual for yogurt, it could be the predicted yogurt. Okay. Or it could be the actual yogurt. Like this bottom value could be just about anything involved with the data. So you really have to pay attention to what that variable is. Now, I'll be honest, most of the time, if you have a graph that uses body weight as the x-axis, it is very common to use that exact same scale and label here, because then you can line up the scatter plot and the residual plot horizontally. Okay, so that's, yes, that is the most common one. In any case, let me walk you through maybe the first three, and then I'm going to give you time to graph the rest yourselves. Okay, so the first person has a body weight of 56 with a residual of 0.85. So if I had to guess, that would probably be right around there. Okay. Next person has a body weight of 80 with a residual of 0.1. So that's 80, and it's barely above the x-axis at 0.17. And I'll do one more. That's our first negative residual, 122 pounds and right around negative 0.4. So that's probably right about there. Okay. Take a minute and just do your best to, it doesn't have to be perfect, just reasonably accurate, graph the other residuals. Okay, so this is what the residual plot should roughly look like. And one thing I want to just make clear is if this is the only thing I had to look at, I could already say whatever model produced this was not the right model. And that's something I want to explain to you all. Part E says, how can the residual plot be used to claim this model is inappropriate? Well, and I will elaborate on what I mean by this. The residuals are not randomly positive and I'm going to take a decent chunk of time to try to dig statements so you understand why I phrase it that way. Okay. Because I used to just say the residuals are not random. They show a pattern. That's how I used to teach this. And a student really helped me learn why that was not sufficient. I'll share that with you all in a moment. Okay. So let me use kind of a couple pictures to kind of explain what I mean by the reason model is not, whatever model produce those residuals is because those residuals do not jump between positive and negative randomly. So you'll notice you have a couple positive, followed by 1, 2, 3, 4, 5, barely negative, the fifth one, and then a couple positive. So it literally goes from positive to negative to positive. That's not enough switching. I want to see positive, negative, negative, positive, positive, negative, positive, positive, negative. Like I want to see some jumps. Okay. Now here's a little bit of a visual, explanation of why that's true. If you have data, even if it's weakly correlated and it's linear enough, if you fit the correct model to it, that model should fly through the middle of the points. So when it goes through the middle of the points, and it should be in the middle everywhere, it shouldn't like magically curve above the data, okay, and then curve back into the middle. It should consistently be going through the middle of the points. Well, if it consistently goes through the middle, that means you have points above and below sporadically. Does that make sense? So you literally will get positive and negative residuals generated at random. Okay, so it'll jump between positive, negative all the time. And this, by the way, is true even if you're talking about parabolic data. If you have data that looks like this, and I'm talking about if you have found the correct model, because we haven't talked about how to build curved models. But if you build the correct model, well, then again, you randomly jump between points that are above and below, above and below, above and below, above and below. And so you will see the jump negative and positive. Now, again, what I used to say when I was teaching this is you want to see random residuals. I would just stop there. And I would try to be more specific and say you don't want to see a pattern. Let me share with you where this fell apart. And I realized, oh, this isn't good enough, apparently. Imagine this is the y equals 0 line. So that's the x-axis. This was the data that we were looking at on a residual plot. It was positive, negative, positive, negative, negative, positive, negative, positive. That's what we saw. And this, by the way, is exactly what I want to see. This is beautiful. positive, negative, positive, negative, negative, positive, negative, positive. Like, yes, you got two negatives in a row. Who gives a crap? Like, it's basically switching back and forth, back and forth. Perfect. That's what I want to see. That communicates whatever model led to those residuals is doing a good job flying through the middle of the data. Okay. But I have students say to me, Mr. Oben, I determined this model was inappropriate because I see a pattern. Anyone have any idea what they were talking about? Here's your hint. Sorry for the people listening to the video recording. You can't see my face. Anyone see the pattern? Oh, smiley face. Yes, that's literally what the student said to me. I see a pattern, Mr. Oben. I said, what pattern are you talking about? And they said, I see a smiley face. And I go, oh my goodness, I clearly did not teach this effectively. Okay, so I no longer say, are the residuals random enough or do they have a pattern? I say, do they randomly switch from positive and negative? Because that's what you want. Okay, and this definitely does that. Okay. All right, let me get rid of this. The green notes are basically things that I've already elaborated on. That's just for people that are watching the recording and want a little more commentary. All right, this next part, part F, so we're almost done with this context. We have a little bit more to dig at. It says, Mr. Oben, again, 220 pounds, got 12.6 ounces. Mrs. Oben, 132 pounds, got 8.4 ounces. Graph their points on the scatter plot, then calculate and graph the residuals. I'm going to give you all a chance to, let's ignore the graphs for a minute because I want to walk you through that a little bit. I would like you all to simply calculate their residuals. Take 3 minutes, find the residual values for both myself and my wife. Get going, please. All right. This is your opportunity to ask questions. If you see anything that you don't agree with, for myself, the residual was negative 0.62. For my wife, it was negative 0.49. All right, so it's worth noting before we take, I asked you a worry graph. Both of us have negative residuals, so we got less than the model predicted. So both of our points should be under. So when you go to the curve and you try to estimate where is 130 pounds, where is negative 0.49, I'm not looking for perfection. I'm looking for something reasonably accurate. Okay. And the one thing I will be critical on is, do you have a point that is under the line? And that applies to both my wife and I had negative residuals. So again, not looking for perfection, but I would be looking for something that is reasonably close to reality. And the one thing I would be picking on is the points are under the line. Okay. Same thing with the residual plot. If you come here and you kind of visually estimate where's 130 pounds, where's 220 pounds, and then you graph, the thing I'm going to be picky about is that both of our residuals are in the negative. Okay, absolutely, I'd be looking for that. Okay. All right, so we did a residual plot. We've learned how a residual plot can be useful to us. We're going to look at one other problem example. I know that there's one other question at the bottom of the page. I will admit the only reason I include this question is so I can needle my wife a little bit. It says, discuss who got more frozen yogurt, both literally and relatively. So obviously, I literally got more than her. I got 12.6 ounces. She only got 8.4 ounces. But can anyone explain to me why in the world would I be deluded enough to think I could argue that I actually got less ice cream? So it absolutely is related to body weight. But what statistic did we just calculate and graph? The residuals. So you'll notice mine is a bigger negative residual, and that absolutely accounts for body weight. That's where it came from. Prediction was made based on body weight. So you could actually argue, well, relative to our body weight, I actually got less because I was further below expected than she was. Okay, so that's sort of the ludicrous argument that I'm making here. Okay. Questions? All right, now, as I said at the beginning of the period, I am not planning to spend in-class time on 3.216. We're going to go right to 17. The reason for that is because, in my opinion, the material covered on 3.216 is redundant enough. There's nothing new there. It's a good opportunity for independent practice. So I am including the answer key in full in this video. These same pages will also appear in the Canvas notes. I am recommending that if you find the time, I even included a step-by-step guide on how to use the graphing calculator if you want to know how to do that. But I would really recommend trying problem 3.2 on your own time for extra practice. Okay, but for now, I want to end on 3.217. We're going to start on part A. I'm going to give you some background information on the context after I give you time to work on it. Part A is just another opportunity to prove that you can convert summary statistics into a linear model. Okay, so use the formulas that we've talked about on the sheet. Slope is r times sy over sx, and then you can use the mean point to find the y-intercept. Okay, go through that process to find the linear model, and then we only have a few short questions to end on, and we'll be done for the day. Get going, please. All right, I gave students what perhaps wasn't quite enough time to finish part A, but I want to wrap up with the parts on the next page here. Once again, part A is using the summary statistics provided to build an equation. The reason I know to put that fraction in that particular order is because looking at the graph, I know I'm using pressure to predict adsorption rate. Quick side comment in case anyone suspects that's a typo, because I certainly did the first time I saw the word. It's not a typo. It is meant to be adsorption. The difference between absorption and adsorption. Fun fact about charcoal, if you were able to shrink yourself down to a microscopic level and crawl along the surface of charcoal like it was a planet, it would basically feel like it's made of just a ton of intertwining noodles and tubes. Okay, just tons of caves and tubes all over the place. And what that means is it's a ton of surface area that charcoal naturally contains because it's so porous. This is why it's used as a filtration system. Because if you pump a gas through charcoal, the gas has so many different surfaces to stick to. That is not to be confused with absorption. When a material sticks to another material, that is called adsorption. Okay? In any case, getting back to the actual problem, again, I know to put the standard deviation of adsorption rate on the top of my fraction because that is the thing I'm trying to predict. Now, that only gets me this far. I still don't know what the y-intercept is. Let me zoom in on that a little bit more so it's easier to see. There we go. But I do know, excuse me, that if I plug in the average pressure of 43.3, this model should predict the average adsorption, 375. This is what allows me to solve for the y-intercept. Questions? Okay. Go ahead and turn the page. I'm not going to torch you all and go straight to the bell, but I do want to get the next two items completed. And then I'll ask you all to just try D and E on your own time another time. Okay. So part B says predict the adsorption rate if the relative pressure were 90%. We're at a point where this should be a very straightforward task. Use the model you just got, plug in 90. Boom, you're done. Okay. Here's the nice thing, by the way. Even if you have no idea how to do part A, you can't get a model, make one up. Make up a model, even if you know it's wrong, and then use it in part B. You'll get full credit in part B, even if the prediction you make is wrong, because the process you followed was correct. This is how the AP exam is graded, which is why I will tell you over and over again when we're getting ready for the exam, if you don't know how to do one part, that doesn't mean you stop. You make up an answer and then use it for the future parts. Okay, the parts are disconnected enough that they just want to see what you can do. They're never going ever. They will never give you a problem on the AP exam where if you can't do A, you're screwed. You can't do B, C, or D. They're not going to design a question that way. Okay. Now explain why this prediction is invalid. Again, what I'd like you to point out, what I'd like you to notice is that even if you can't see the bend in the data, and it's there, it's just really, really hard to see. The first couple points have positive residuals, as do the last couple points, but all of these points are under the line of best fit. I wouldn't expect you to see that until you look at the residuals. And then you can clearly see the data is curved. There's no denying it. The residuals zoom in on the relationship between the lines and the points, or the line and the points. So what I would say is the residual plot is not random, so this model is inappropriate. I don't care what model was used to produce it. Despite the fact, I don't know if you noticed, the R value is unbelievably strong because the data is so barely bent. But my response is there's clearly a better model out there. Okay. Also, we once again are extrapolating. The highest pressure in our data set was 82. We just made a prediction at 90. And so we're extrapolating beyond the domain of our, okay? All right, so students have left for the day. I was rushing a little bit, but I wanted to make sure I included D and E in the video. So what may make this prediction seem valid? I alluded to that briefly, and that was the fact that the correlation is so unbelievably strong. If that's all you knew, that there was a relationship out there that was really, really strong, that might make you instantly assume that whatever model was used is going to be an appropriate model. But unfortunately, this data looks linear enough, and yet it is slightly bent, and the residuals magnify that bend and make it clear. So I could certainly look at this data and say, well, the data looks straight, and the R value is really strong. But both of those items are actually tricking me because in the end, the residual plot is not random enough. And so whatever model was used to create those residuals is not appropriate. Okay. Now, in terms of suspecting if this prediction is too high or too low, I would say, again, this is in light of the residuals. You'll notice that for the higher pressures, it looks like pressures above, what is that third point? 66. So at 66 pressures and above, the residuals seem to be positive because the points start to bend above the line. So my suggestion or my assumption is that the prediction is going to be under the curvature of the points, that the true points would be higher up. So my belief here is that we would end up under predicting the true value. And again, I cited, it looks like I estimated it from the graph. I could have pulled that number directly from the table, but it happens around that value. All right. So that is it. Thanks for watching. Have a good one.